So welcome to the next section in fluid statics. In this section we will study how to measure the change in pressure due to the change in elevation of any element in the body of the fluid. So in order to understand, let's see this figure in which you have a tank of water, and if you see elements as A, B, C and D, all of them may experience different pressure due to different depth in the water. So as this, if you see here point C and point D, they are almost at the same depth. So their depth is same, so they will be experiencing the same amount of pressure. But as you go more deeper in the pond or tank, your pressure on this element will keep on increasing. So in order to measure in this pressure, change in pressure, we need to develop some equation. So let's assume that in a dam, at the back side of the dam, there is a water, and consider a fluid element from that water pond as this small element, and let's develop an equation which is named as hydrostatic equation. So hydrostatic equation is the base for the fluid statics. All equations are based on the hydrostatic equation. So just sketch a free body diagram. Let's sketch a free body diagram and see the forces acting on this small element inside the pond of water or the dam. So if you see, this element is being applied by a force in with EA, and in this direction, after a step of, let's say, delta L length of the element, it is experiencing a force of P plus delta P into delta A. So consider a static body of fluid as shown in this figure. So the cylindrical body is isolated from the static water behind a dam. As free body diagram is shown, delta L is the body length, delta A is the cross-sectional area. Body is inclined at an angle alpha with the horizontal, right? So if we apply the force equilibrium in the L direction, we will say that summation of all the forces will be equal to 0. So one will be pressure force on this cylindrical body, and the other will be the weight force. So let's put them all together. For pressure force is pressure forces are equals to weight forces, and then you bring them on the opposite side of the equation, and the equation goes like this one. So then insert the values for pressure force and the weight force, which gives us this equation, which this is the pressure forces acting on this surface and the surface at delta A or delta L length. The weight phase force which is acting is given as gamma V into sine alpha, because it is inclined from the horizontal surface. So sine alpha is coming in. This is delta A, and delta V is the volume, and gamma is the specific weight of the water. So solving this equation, we end up with another equation. Just and then if we divide that equation by delta L, we will get net equation as delta P over delta L is equals to gamma minus gamma sine alpha. Now sine alpha is again can be expressed by trigonometric relationship, that sine alpha is perpendicular equals to perpendicular over hypotenuse, right? So let's apply this formula in here, and if you see here is delta Z, height for the element, and delta L is the length of that element. So delta Z by delta L will be replaced by sin alpha, which you can see here, and insert this one in equation 2, and we get relationship like this. And then delta L will be cancelled by delta L, and we will be coming up with this equation delta P over delta Z. So applying the limit as delta Z approaches 0, as delta Z approaches 0, right, we will get a differential form of equation which is written by this form. Means changes in the pressure correspond to the changes in elevation. Because if you write this equation as dP is equals to minus gamma over dz, right? So this negative sign indicates that as the depth will decrease, the pressure will decrease. So as the depth will increase, the pressure will increase. So we can apply this equation to the particle shown in this pond, where the only forces are the pressure forces and the weight. If one travels upward in the fluid can be water, fluid can be air, in positive z direction, the pressure will decrease. If one goes downwards in z direction, minus z direction, the pressure is going to increase. If one moves along the horizontal direction, horizontal plane, the pressure remains constant. So if anybody is moving like this, the pressure will remain constant. These pressure variations are exactly what a diver experiences when ascending or descending in a lake or a pool. So just imagine if a person is standing here, right, and he just jump in water. So as soon he is going down, down and down and down and down, the pressure on his body is going to increase. So in reality, you can see, for example, if a boat is on the sea, it is experiencing atmospheric pressure, right? But submarine, as it goes down beneath the seawater, it experiences more pressure than the atmospheric pressure experienced by this boat. Similarly, if we go up in the aircraft, so the pressure upon us decreases as we go up in the height. So that's why, I mean, we can apply this hydrostatic equation relationship to measure the variation of height on pressure. So then another thing is the piezometric head and piezometric pressure. If you see here, as we saw that pressure, simple head and simple pressure changes as the depth of the point changes in the tank. But what about piezometric head and piezometric pressure? So it says that piezometric pressure and piezometric head remains the same as long as the liquid is same, which means that piezometric head of A will be equal to piezometric head of B will be equal to piezometric head of C, right? Whereas H piezometric C is not equal to H piezometric D, just because the fluid is changed from water to oil. So piezometric head will be same for E, D and F, which is not the case when you have only head. So there are two things. One is simple head, which is not same in one liquid, right? Which is not equal to H, C or D. But if you see piezometric, they are the same. So hydrostatic equation is used to predict variation in the fluid with a constant density. So when we say the fluid is same, the density is constant. So assuming specific weight is constant because the density is constant, so integrate this equation and you will end up with a simple relationship, which is P is equals to uh, gamma Z, right, is equals to constant, where this terminology is equals to piezometric pressure, where Z is the height, simple elevation on the or vertical distance above fixed reference point called the datum, and Pz is the piezometric pressure. Similarly, if you divide the equation by specific weight, you will end up with this term, which is again can be written in this piezometric pressure form, right, which is again constant and is named as piezometric head, where Hz is the piezometric head. Since Hz is constant, right, because in one liquid, if in one fluid, so we can say that Hz must be equal to Hz2. That means Pz P1 over gamma plus Z1, P2 over gamma plus Z2 must be equal. This means that head at one point must be equal to piezometric head at second point. Or in other terms, piezometric pressure in one fluid must be equal to piezometric pressure in that same fluid at point 2, which gives us a general relation delta, which we can say delta P is equal to minus gamma delta Z, where delta P is P2 minus P1 and delta Z is equal to Z2 minus Z1. The hydrostatic pressure is valid for the hydrostatic pressure equation. Hydrostatic equation is also valid for any constant density fluid in hydrostatic equilibrium. So in conclusion, we can say that piezometric head is written as Hz is equal to P over gamma plus Z, where piezometric pressure relationship will be given by this equation. So if we summarize them, we can end up with this equation, which is Pz is equal to gamma Hz in terms of piezometric head and piezometric pressure. So piezometric head and the density of the fluid. When the hydrostatic equilibrium prevails in a body of the fluid of constant density, then Hz will be constant at all locations, as I showed you in the figure. Piezometric head is constant in water. Yes, piezometric head is constant in oil, as you see in this figure, that all these piezometric heads at these 3 points will remain same, and at these 3 points they will be equal to each other, right? Notice piezometric head is not constant when density changes from oil to water or vice versa. As you move in there, piezometric head will change. So we can say that Hza is equal to Hzb is equal to Hzc, Hzd is equal to Hze is equal to Hzf. So Hzc is C must not be equal to Hzd. So in conclusion, we have hydrostatic head, we have hydrostatic pressure, we have hydrostatic equation. Hydrostatic equations involve piezometric head and pressure can be given as this Pz is equal to P plus gamma Z. In terms of piezometric head can be written as Hz is equal to P over gamma plus Z. So let's look at the example. What is the water pressure at the depth of 35 feet in the tank shown when water at 50 degrees Celsius has specific weight of 62.4 pounds per feet square? So let's see on the solution. Given information is this, that P1 at the atmosphere is 0 gauge, pressure, because the gauge pressure is 0 at this point at atmospheric pressure. Z1 is 250, Z2 is 215, as you will subtract minus 35 from 250, so you will end up at 215 feet at this point. So applying hydrostatic equation, you will insert the values. Z1 is here, Z2 in here, P1, this terminology will go 0, right? So you will end up with this form of equation, and then you can just simply multiply and add, and you will get the pressure at point 2 at this point, which is 2180 pounds per square feet gauge. In terms of inches, it will be 15.2 pounds per square inch. So this example is for one single liquid, right, wherein we can measure the hydrostatic pressure and hydrostatic head. Let's look at example where we have two different kinds of liquid and both have different densities, right? Oil with a specific gravity of 0.80 forms a layer of 0.9 meter deep in an open tank that is otherwise filled with water. The total depth of the water and oil is 3 meters. What is the gauge pressure at the bottom of the tank? What is the gauge pressure when Z3 is equals to 0? Right? Because the total height is 3 meters, so here Z3 will be, so look at what we have provided with. We have water at 10 degrees Celsius with specific weight 9,810 newtons per cubic meter. Specific gravity of oil is given, from which we can calculate the specific weight of the oil. We know the pressure at point 1 is 0 gauge pressure. Z1 is 3 meters and Z2 is 2.1 meters. So applying the hydrostatic equation, we will able to solve this numerical as well. So just for the gamma of oil, you will multiply S of oil with gamma of water, and you will get the value of oil. So insert the values, and simple multiplication, addition and subtraction, you will get the value of pressure at point 2 here, which will be equal to 7.063 kilopascals. So note that the pressure experienced here will be the same pressure experienced here, but when you will divide this pressure by gamma, you will get a different PZ value, which is piezometric pressure. So at the oil water interface. Now apply hydrostatic equation in water and insert the values in therein, you will get P3. So simple multiplication and subtraction and addition, you will get the value of P3, which is 27.7 kilopascals, will be the pressure at Z is equal to 0 meters at the datum, right? So this will be your value of pressure. By this, I would like to thank you. Thank you very much.